Hello, my name is Manuel Veiga from PicoQuant. My colleague is Laura Lleras from Nikon Instruments Europe. And in this video, we would like to show you how to make FLIM measurements with a Nikon A1 RS upgraded with LSM kit from PicoQuant.
We are going to use these elements, the Nikon software, to acquire a confocal image using, in this case, Galvano, seen here. But you could also use resonance scanner very easily by just pressing. We have different optical configurations here, so you can switch easily from FLIM to FCS, resonant or Galvano confocal imagings. If we press start here, you can see we are going to acquire an image using the DU4 detector that has, in this case, 2 PMTs and 2 GASP detectors, which are highly sensitive. And you can see here our daisy pollen. In this case, we're going to acquire a set stack, so we're going to use ND acquisitions shown here. We have already established the top position and the bottom position. We're going to do 20 steps. In this case, we just press run now. This will take 20 seconds to acquire the whole set stack, and at the end we can have a 3D acquisition. Okay, here we have our image, all of the different set planes shown here, and if we press this button, we have the 3D visualization of the whole set stack of the daisy pollen. Everything done very simply by just clicking one button.
So as Laura explained, the NIS software allowed us to prepare several optical configurations, which is the measurements. So for FLIM, the only thing we need to do is to select the FLIM optical configuration. And when we activate it, we see that we have monodirectional scan. We have a moderate scan speed. The detector is set to the auxiliary port. This is where the PicoQuant detector is sitting, which is connected to the time-correlated single photon counting board. And when we look for the excitation part, we see that the second port is activated. This is where the pulse lasers from PicoQuant enter the scan head. So for making a FLIM image, the first thing to do is always to make a test measurements so we can control the repetition rate of the laser and also the count rate of our sample. For that, the only thing we need to do is press scan. A test measurement is initiated in the SymphotIme software. To control the repetition rate, we can go to the time-correlated single photon counting tab. We see that now we are exciting with 20 megahertz, but we see here that most of the bins are not occupied, so I will increase it to 40. So this is looking better. And to control the count rate, we go to the image tab, and we see this red line here. This red line here sets the pile-up limit. So the idea is to optically tune the laser to have all those spikes just below that line. These spikes, they can be set to the pixel width, so to the pixel dwell time. So therefore, each spike corresponds to a pixel. So now we have everything below the pile-up, so we can measure. So I stop the test measurement. And for capturing the image, I can set here the condition to finish. This was set to, in this case, 2,000 frames. So I would change it to maybe 2,000 counts. That makes more sense. I can put the name. This would be daisy pollen. And I can just capture. The image is started in the SymphotIme software. So at the same time, the image is being acquired. We can play a little bit with the contrast and with the brightness to see if we have a nice FLIM image. So we have reached 2,000 counts in the brightest pixel. So the measurement comes to its end, and it's automatically saved in the SymphotIme software.
In this case, we have an optical configuration that is doing FLIM in the SymphotIme. here, but at the same time, these elements for Nikon is acquiring a transmission image, as shown here, and you can play with the gain and the offset to make it better. This is very useful because then you can compare the results for FLIM and transmission.
And as easy as measuring a FLIM image is also to make a FLIM set stack. So the only thing we need to do is, in the same FLIM configuration, activate the ND acquisition mode. We can give a name to the set stack where all the different layers will be saved. I will call it set stack. Then the name for the different layers, this is daisy pollen. And we just click run. Here in the set stack, each layer will contain 5 frames. So, and the measurement has finished now, and we have all our layers of daisy pollen saved automatically in the SymFotime software for analysis.
As Manuel said before, he actually showed a very simple experiment, but with these elements from Nikon, we have the capability of doing more complex experiments. This is done by the jobs model, where actually you can choose different cells, do an acquisition in confocal. It's fully integrated with FLIM and FCS, so if one of the cells of interest is selected, you can actually do automatic FLIM and FCS without having to be there. It's all automated.
So if what we want to do is FCS instead of FLIM, then what we have to do is to change here for the configuration. We have 2 FCS configurations. One is for excitation with continuous laser from Nikon, and the other one is for pulsed lasers from PicoQuant. So we'll choose one with pulsed laser from PicoQuant. So we see here that in the A1 Plus aux control, we have switched to FCS already. And the NIS software allowed us to do like a 3-point, like here, for example, or even like arrays of like 2 by 2, like in this case, or even higher than that. So we'll just make a simple experiment. We have Atto-488 dissolved in water and nanomolar concentration. And I will measure each point to make it short for 10 seconds each. I will remain as Atto-488. And to run the experiments, I don't have to click capture. So we see that in the SymFotime, the measurements are initiated. And as soon as the measurements are finished, they will be automatically stored in SymFotime software.
Okay, thank you very much for watching this video. For any further questions, please contact your local representative for PicoQuant and Nikon, and the best of luck in capturing any images.